thanks for watching, and today I would like to tell you about the awesome Lagrange Interpolation Formula. And it's awesome because finally after 10 years I understood it, and it's great, I promise. And the question is, find a polynomial of degree 2, so a parabola, that goes through the following 3 points. So we will indeed show that if you give, let's say, n plus 1 points, there's a unique polynomial of degree n that goes through those points. Like for example, in terms of a picture, we have the points 1, 2, then 2, 3, and then 4, 11. And we can actually show there's a parabola that goes through exactly those points. In fact, there's exactly one parabola with those points. And it's all based on the Lagrange Interpolation Formula. And I will give you the formula with an example first, and then I will tell you why this works. So what does Lagrange say? Really smart guy. I mean, you know, there's also Lagrange multipliers, lots of Lagrange polynomials and all this stuff. So he did a lot of stuff. And how do you do it? So it turns out P, the polynomial, is given by an explicit formula, and it's very neat. First of all, we have the outputs, 2, 3, and 11. So it's 2 times something plus 3 times something plus 11 times something. Then you do, because you want to have a polynomial of degree 2, you do x minus something. X minus something, x minus something, and then x minus something, x minus something, and then x minus something, x minus something. And usually it's written as this really abstract formula, but let me make this concrete. What this says, formula says, is first of all, ignore the first point 1. Okay, so ignore that, and let's do x of all the other points. So x minus 2 and x minus 4. And then, for the second one, ignore the second point and do x minus 1 times x minus 4. And lastly, ignore the last point and you do x minus 1 times x minus 2. And then, here's where the fun starts. So it's still something minus 2 and something minus 4, except now we put, because we ignored the first point, we plug in 1 here. And it makes sense, because if you plug in 2 or 4, you would get 0, and you would divide by 0, which is a problem. And same thing here, you repeat this, something minus 1, something minus 4, but the only choice you can really put is 2. And lastly, also something minus 1, something minus 2. And the only choice is 4 in this case. And then you calculate that and you expand it out. So if you do that, 1 minus 2 is minus 1, 1 minus 4 is minus 3, so you get 3. So 2/3, and you expand that out. So x squared minus 6x plus 8. And then this becomes, I think, minus 2, so minus 3/2. If 3 over minus 2. And then x squared minus 5x plus 4. And lastly, 11. And I think this is 6, so 3 times 2. And then x squared minus 3x plus 2. And then you want something quadratic, so you factor out the x squares first. So it's x squared, so 2/3 minus 3/2 plus 11/6. And then plus x times, in this case, so minus 6 times 2/3, I believe it becomes minus 4. And then you get something ugly, so minus 15 over minus 2, so 15/2. And then something even worse here, I think minus 11/2. And lastly, you do the other term, so I think 16/3 minus 6, and then 11/3. So you get this ugly polynomial, but here's a beautiful thing. if you actually do the algebra, it gets simplified. So in the end, if you do this, you just get x squared minus 2x plus 3. So this polynomial is x squared minus 2x plus 3. And you can indeed check that, it goes through those points. So P of 1 would be 1 minus 2 plus 3, and that is 2, just like we wanted. P of 2, it's a 4 minus 4 plus 3, which is indeed 3. And maybe the non-obvious one, P of 4, that's 16 minus 8 plus 3, and then drum roll, that's 8 plus 3, which is 11. Okay, so you see it works. It gives us an explicit formula, which is very rare in math, that gives you precisely a polynomial of a certain degree that goes through some points. And again, nothing special but the quadratic part. You would just, if you want a cubic polynomial, you would just repeat the same thing over and over again. And now, let me just do a couple of theoretical remarks, because this is cool in computation, but also in theory. Because it combines some very neat linear algebra. First of all, where in the world do those coefficients come from? So where does this Lagrange polynomial come from? So remarks, so first of all, motivation. So P, all right. The first part is not too bad because the x's, ideally what we would like is something that evaluates to 0 at 2 and 4. So we do x minus 2 times x minus 4. And then suppose we have this. P is a1 x minus 2 times x minus 4 plus a2 x minus 1 times x minus 4 plus a3 x minus 1 times x minus 2. So I think that part isn't too bad. The reason why we guess those polynomials is because if you plug it at 1, 2 of them just become 0, and you're left with this one. If you plug it at 2, 2 of them are 0, and then the other one is non-zero. So it's really an expression that's nice when you evaluate at the roots. But the question is, how do you get those other terms? Well, remember what you want. You want P of 1 to be one of your roots. So if you evaluate that, then we get a1 times 1 minus 2, 1 minus 4, plus a2 times 1 minus 1, which is 0, and a3 times 1 minus 1, which is 0. So if you do that, you're just left with a1 times 1 minus 2 times 1 minus 4, which tells you precisely that a1 is your polynomial at 1, which is 2, over 1 minus 2 times 1 minus 4. So in this case, we have 2 times 1 minus 2 times 1 minus 4. So this is where this weird coefficient comes from. It's just from the requirement that, P of 1 has to be our value, and 2 of the 3 terms cancel out. That's why we have this. And you can just continue. You see P of 2. What happens then is that this term becomes 0 at 2. So 0 plus a2, 2 minus 1, 2 minus 4, plus 0. And so a2, what this becomes, it's 3 over 2 minus 1, 2 minus 4. So in the end, what you get is our Lagrange multiplier formula, which is, again, I want to remind you, it's P equals to this term, so really 2 times x minus 2, x minus 4, over 1 minus 2, 1 minus 4, plus 3 times, again you ignore the second root, x minus 1, x minus 4 times this term, you see 2 minus 1, 2 minus 4, and the last term plus 11 times, x minus 2, x minus 1, x minus 2 over 4 minus 1, 4 minus 2. So this is where the coefficients come from. The idea is, let's suppose P is a linear combo of those nice polynomials that vanish at a lot of points, and those coefficients, you can just deduce them from this part. That's one thing. This is how you get the coefficients and therefore the formula. And the question is also, was there anything special about our polynomial? In other words, can any polynomial be written in this way? And the cool thing is, the answer is yes. And this is where awesome linear algebra comes in. So claim any polynomial, in fact, can be uniquely written. Written in this way. So it's interesting. The question was, can be written in this way? It's a question about span. But let's show the opposite. Let's actually show that those polynomials are linearly independent. So claim x minus 2 times x minus 4, x minus 1 times x minus 4, x minus 1 times x minus 2 is linearly independent. And the proof is awesome sauce. So suppose that, let's say C1, x minus 2 times x minus 4, plus C2, x minus 1 times x minus 4, plus C3, x minus 1, x minus 2. Is the zero polynomial. Again, this is an identity that depends on x. So let's plug it in at the values. If x equals to 1, we get C1, 1 minus 2, 1 minus 4. And you see, this is precisely non-zero, because we assume that our points are distinct. At least the x values are distinct. And look what happens here. If you plug in at 1, this whole term becomes 0. So you get 0, and again, also with this term, equals 0. So what you get is, you get C1 times a non-zero number is 0, so C1 is 0. And similarly, if you plug in x equals 2, this vanishes, this vanishes, this does not vanish, so C2 is 0. And lastly, or x equals 4, you get C3 is 0. And therefore we're done. We assumed some linear combination gives you the 0 vector, and we showed that the coefficients are 0. But how in the world does that show us it spans? Here's the cool thing. We have this linearly independent set with 3 vectors. So beta is linearly independent and has 3 vectors. And the fact that it has 3 vectors is important because it's precisely the dimension of the set of polynomials of degree less than or equal to 2. So here's the cool thing. If you have a linearly independent set that has as many vectors as the dimension of your space, it spans, and therefore is a basis. So beta is a basis and spans P2. In other words, not only any polynomial of degree less than or equal to 2 can be written in terms of those Lagrange polynomials, but it can also just be uniquely written, which is insane. And again, we barely did any calculations. It just follows from a mastermind of linear algebra. That's why I emphasize, even if you do numerical calculations, it's important to know theory, because theory gives us those nice results. And by the way, proof of this result, I've done a video on the replacement theorem. You should check it out. That's good. And just two more remarks. So it turns out this basis is also very important for like more advanced linear algebra, which I have yet to learn. So take this set, and we've just shown it's a basis. So x minus 2 times x minus 4. Let's scale it. 1 minus 2, 1 minus 4. X minus 1, x minus 4. 2 minus 1, 2 minus 4, and x minus 1, x minus 2. And then 4 minus 1, 4 minus 2. So we have just shown it's a basis, except for the scaling factors, which don't matter. But it turns out this is actually a very nice basis, because if you let that to be P1, P2, P3, well, notice P1 at 1, that's just 1 minus 2 times 1 minus 4 divided by this, which is 1. P1 at the second root, that's 2 minus 2, which is 0. P1 at the third root, that's 0. And sort of similarly with P2. P2 at 1 is 0. P2 at 2 is 1. P2 at 4 is 0, and P3 at 1 is 0, P3 at 2 is 0, and P3 at 4 is 0, and 1, sorry. So in particular, what you get is some sort of an identity matrix. So indeed, Pi of xj, where Pi is your ith polynomial, xj is your jth root, is just delta ij, which means it's 1 when I equals j, and it's 0 everywhere else, and has something to do with dual bases. Again, let me learn a bit about dual spaces, and I can tell more about that. Lastly, I want to show you this really cool fact, which maybe you were used to it, and you used it a lot, but now we can actually prove it. Namely, a really cool corollary. If you have a polynomial, let's say in P2, and it has 3 roots, in this case, let's say roots 1, 2, and 4, then the only polynomial in this case is the 0 polynomial. So, and indeed, you can generalize this easily. What you can show in general is that any polynomial of degree n, so if the degree of p is less or equal to n, and p has n plus 1 roots, then p has to be the 0 polynomial. And it follows from the Lagrange Interpolation Formula. So, because remember, we had the previous set was a basis, so you can write P as any linear combo of those nice polynomials. So C1 of x minus 2 times x minus 4 plus C2 times x minus 1 times x minus 4 plus C3 times x minus 1 times x minus 2. Again, this set spans P2, so any polynomial, you can write it of this form. But then suppose P has roots 1, 2, and 4. Then P of 1 is 0. But also, P of 1 is C1, 1 minus 2, 1 minus 4, plus C2, 1 minus 1, which is 0, plus C3, 1 minus 1 is 0. So in particular, since this is non-zero, we get C1 equals 0. And you can do the same thing. P2 is 0, and this is some form with C2, and then you get C2 is 0, and lastly with P4, and you get C3 is 0. So what does that tell you? P is 0 times this, plus 0 times this, plus 0 times this. And that's just a 0 polynomial. So how cool is that? Now we can sort of sleep in peace. So that's good. All right, I hope you like this Lagrange extravaganza. If you want to see more linear algebra and more math, please make sure to subscribe to my channel. Thank you very much.